believer in program verification, and he spent the last couple of years mostly working on the VCC tool, a verifier for concurrent C programs. And today he's going to talk to us about reasoning about weak memory models.
Well, not about models, programs. So we'll just go to slides if you need details, because I want to try to keep this sort of like dessert. So let's just start with the very basic example, which drives almost everything. We have two threads. I won't bother labeling them, but we have this thread writes to X, and then say it reads from Y. Okay, and this thread does the opposite. Okay? Everyone understand the program? So these are assignments. I'm just using an arrow because colon equals looks a lot like equal on a blackboard, right? Okay, everyone, so here's one thread, here's the other thread. Good? Yes, so this means check that Y is equal to, read Y, check that it's equal to 0, or else you can't go on. Okay? Everyone good with this? So, does everyone know what sequential consistency is? Yes? Good. So, in a sequentially consistent memory, is it possible to finish both of these threads? Who says yes? Anyone? Anyone say no? No. Because you see... Oh, go ahead. The checkbox?
Blocks, like the
Yeah, this, you get stuck here. You can't move past if Y isn't 0. So sequentially, in a sequentially consistent memory, you get stuck because one of these has to do its assignment first, and whichever one does its assignment second won't be able to do its test. Good? So this is clear. Now, in weak memory, how many of you are familiar with sort of weak memory models a little bit? Wow, that's surprising. Good. So in weak memory models, even, and by weak memory model, I mean anything that's weaker than sequentially consistent, okay? In weak memory models, typically something like this can complete, right? Because these writes don't have to be seen in the same order in every thread. So this thread would see his write here and maybe Y's write there, and this thread would see Y's the write to Y here and the write to X there. Good? So for example, this can happen on an x86. If you have store buffers, you put this store into the store buffer, and then you read from memory, and meanwhile the other thread does the opposite. Good? Yeah, we're always assuming values are 0 initially. Okay? So, now the problem is, what do we do about weak memory, right? Well, first of all, does everyone understand why we would want to program to weak memory, right? That's what hardware provides. And hardware provides this weaker memory because it's more efficient. And today, basically, our state of the art in programming is we're just throwing up our hands if we can't get to sequential consistency. So what you will normally do is simply add stuff to your programming discipline or to your compiler to make sure your programs are sequentially consistent, right? So, for example, a compiler would normally, if you wanted to make this sequentially consistent, either the programmer or the compiler would add a memory barrier here. So in the case of x86, it would flush this store buffer, and over here it would also flush this store buffer. And in fact, by the way, everything's volatile today, so don't worry about stuff that's ordinary sequential writes or anything like that. In fact, a discipline that does it is that between any volatile write and a subsequent volatile read, you have to flush the store buffer. That gives you sequential consistency, but at a price, right? And that price can get to be expensive, and it costs you cycles and it costs you energy. And there are a lot of common places where you don't need this at all, even though you might or might not be familiar with it. For example, producer-consumer, with a ring buffer. You don't need any sequential consistency. Just acquire-release is fine. Implementing locks, you don't need it, right? So many, many places. So we would like to actually let people program to weak memory, actually have programs that won't be sequentially consistent. But the problem is, where's the methodology? We don't have one. Well, what would be a decent programming methodology? How do we like to reason about programs? We like to reason about programs with invariants, right? Ordinary invariants talking about the global state, okay? Now, just for illustration, we'll go ahead and think in terms of a wiki-grease. Is everyone familiar with the wiki-grease method? Is anyone not familiar? I'll explain it. So here's the idea. The idea is we go ahead and choose what's true here, like an assertion. So just like with, this is for sequentially consistent memory. You put an assertion here, assertion here, assertion here, at every control point, okay? And the requirements are that it has to be locally correct. That is to say, from whatever you write here, doing this assignment, it has to give you whatever assertion you write here, okay? Just like sequential programming. And the additional thing you need for concurrency is called non-interference. It says that if you start out in satisfying whatever assertion you have here, say, and you're about to do an assignment from another thread, assume what you have here and what you have here, okay? Do the assignment and prove that this is still true. So interference from someone else preserves whatever you have here, and you get to use whatever's up here also in proving that. Good? That's a wiki-grease, okay? We're going to use essentially a wiki-grease with only one little minor modification that we won't need to see for a while. But let's just look at this program. And suppose we wanted to prove that this thing couldn't get to the bottom, right? Can someone help me how to prove this? I want to prove false down here. So we'll get a thing here, and their conjunction should be false. So we would have to come up with an annotation for this program to get false down at the bottom. Well, we could sort of imagine what we could put. Up here, what's the strongest thing we could possibly have? Ignoring just the type information, like x and y are each 0 or 1. X is 0, that's all we'll know. Well, no, here we can't say y is 0 because it would fail non-interference from here. So here's just x is 0. Here is x is 1. What about here? X is 1. We can't do any better, right? So we'll get x is 1 here, we'll get y is 1 here, and the post condition is they're both 1. Well, that's okay for weak memory, isn't it? Right? So what went wrong, right? I mean, it seems like we can't. Why can't we?
After both y equals 0 and x equals 0, you can assert y equals 0, right?
It's not stable. It will fail non-interference. Everyone see? We know x is 1 here, but we can't add y is 0 here because this would break it. Okay, so what you're suggesting is that we add additional variables, auxiliary variables. So here's the thing. If we don't add any auxiliary variables, we can't prove this. Period. There is no annotation. And in fact, a wiki-grease is completely sound for acquire release. There's nothing wrong with it. So maybe, maybe weak memory isn't such a bad thing. Maybe we can program it just like normal, right? Well, if it was sound for weak memory, at least we would have a way to a decent methodology, right? I mean, Well, we could consider completeness as an issue, and you're right, so far it isn't quite complete. But even just considering soundness, there's sort of something suspicious, because most of you probably know a wiki Greece is complete for sequentially consistent memory, right? However, that completeness result requires the use of auxiliary variables. I'll call them ghost variables, just because I like the word ghost better. So apparently, by restricting the way we are allowed to use ghost variables, we can get a programming logic that still looks like ordinary programming logic, but is sound for weaker memory models. Okay? This is the key. This is the key thing you have to appreciate. And this gives us, a work program, right? See what sorts of memory models can we actually get to by some sort of coherent restriction, or going the other way, take a memory model, see if you can get a restriction on the use of ghosts and perhaps on the structure of invariants that's going to be sound, and as Moshe suggests, you would also like completeness, right? Okay, so is everyone good so far? Now, so let's look at, now I've been a little bit cavalier about saying what the program model actually is here. So just for purposes of description, I'm going to use what's basically the simplest model that has something like acquire release. And here's the idea. The program sort of determines a bunch of edges, a relation which we'll call sequenced before, which just is determined by the program. It says this thing precedes it in every execution. So in every execution, this has to happen before this, and so on. But it doesn't have to order other things. An execution, by the way, there's an initialization, which of course goes to both of these, and these would go back to there. So in an execution, you might add additional edges, because communication might add additional, let's call happens before edges. So if happens before will be the sequence before plus whatever additional edges we choose to add, but will require that these edges be a partial order. Okay, so it has to be transitive. Okay. But we can add as many edges as we want as long as we don't make a cycle. So and now, once you add those edges, you're going to have one restriction. And that is if you have two updates, like these, that conflict, they don't commute, then you'll have to order them one way or the other. Okay? These do commute, so you don't have to have an edge between. So this is, in fact, an execution. The program is an execution. Now, the reason for this definition of an execution is we can define sort of a cut, a partial execution, like a state, by just cutting this, taking some prefix of this partial order. That is to say, any set of operations that are closed up. And now, within that state, we can uniquely determine the value of the state. Take the initial state, which we'll assume is fixed, and then by an execution, and apply the updates in some order consistent with the happens before. Each one gives the same value by that. So they think of this as a function from states to states that just takes the state and changes x to be 1.
The local state?
Yeah.
I have a question just before you go to the lab. So if I take this program and I just rewrite the program explicitly with the buffer slot disaster, like I put the buffer, the store buffer here,
Yeah.
and I just do like each thread has a buffer. So there are two buffers. So
Yeah.
buffer 1, buffer 2,
Yeah.
and then this is of length n and n, and I don't know what n and m are, and then I just x1 becomes stored into the buffer.
And make it sequentially consistent or something.
Yeah, but I'll get a new program, and just on the new program I just use normal.
Yes. So the question is, why don't we just materialize the store buffer into the programming model? Because we are not animals. Does that answer the question? Okay, so this is what separates us from the beasts in the field, or from hackers. If you're a hacker and you're trying to understand how to program, you try to keep track. Oh, what's in the store buffer? Now, suppose you have a function call. Now, you had a function call that used to have a really nice, clean post condition. What does the post condition look like now? Well, there's some sequence of crap in all the different store buffers, and if I were to empty them, I get to the right place. But I have no idea what's going to happen if I read from that state, right? It's complete chaos. No, this is not where we want to go.
No, but the point is that to get something that is equivalent.
We will.
This gives you at least a low-level model.
Yes.
Like to arise above, but it gives you a benchmark to prove soundness.
Well, in fact, this model that I'm describing is in fact sound for that model, for x86 TSO. Okay?
I just wanted to understand the sequence before and happens before that. Once you combine sequence before and happens before, does that would be a global happens before?
That is the global. You take sequence before, you extend it to a bigger relation called happens before. That's it. Yeah. Well, not just transitive closure. You could add edges just because I feel like it.
But I want to go back. You said that when you do x equal 1, x becomes 1. But
Yeah.
that's not what you really mean, because you would question when does it become visible, right? That's the issue.
No. A state is a state. We're trying to think in terms of global states like we used to before this weak memory crap ever showed up.
Okay, so when you say in a weak memory model, this problem can terminate.
So I will describe exactly what the semantics of reads are in a moment.
Yeah.
So each of these things is simply this is just a function from states to states. To say whether this thing passes, you have to say what state does he see? Okay, when you try to execute that read. And the answer is, take the set of all events that precede him, okay, in an execution. Take the set of events that precede him, and now take any linearization of those events and apply their updates. And any linearization will give the same result because conflicting updates have to be ordered. That's the state he sees. For this thing to execute, this thing has to be true in the state that he sees. So in this particular execution, Y is actually seeing, because he doesn't precede him, doesn't happen before him, he sees the original value of 0. If we were to add, in making an execution, an edge here, now this would fail. Okay? Good? Everyone understand the semantics? Okay. Now, we said we wanted to reason about this using a wiki grease. Oh, there was a question.
That sounds as though now it's determined that the program will succeed, will terminate.
With this particular execution, in fact, it will terminate, finish. If I took this execution, it would not. It wouldn't be really an execution, you could say. Okay?
But there are executions of your original program that still get stuck.
Well, the one where I add this, that's an execution, and it's not an execution in the sense that it can't be completed. Okay. So everyone understands the operational semantics. Now, how do we make a programming logic? Well, this thing is just a graph. So to give an annotation to a program, just choose a state predicate for each edge. Okay? Any predicate you want. For any event, call these operations. For any operation, you can define its precondition as just the conjunction of the labels on all of its incoming edges, right? What's the local correctness proof obligation? For every operation, take its precondition. From any state satisfying its precondition, if you execute that operation, you should satisfy the label on every outgoing edge. Everyone get that? See, that's local correctness? Good. Now, non-interference. I've been a little bit lazy about talking about these reads versus writes versus other things. We would like to, one reason for having reads and writes being only slightly different, and we're going to unify them, is we want to talk about programs with ghost updates and ghost updates also. So, in general, an operation is the form of a guard and an update. When I just write this, it means the update's trivial, the identity. When I just write this, it means the guard is trivial, the predicate true. Okay? But I could have something like y equals 0. If that's true, then x gets 5, or some ghost gets 6. Or I could do several assignments. I could even do a read, modify, write over here. Anything in this, any function of the state. This separation of the guards and the update is important. And here's why. The non-interference condition, here's the simple version of the non-interference condition. Simple version is that for any operation of the program that's potentially concurrent with that edge, that means that it's neither ordered before here by the program nor ordered after here by the program, so it's potentially concurrent. You get to use the regular non-interference rule, but you don't get to assume the test. You only consider the update. Okay? So it's just when you're doing non-interference, you ignore the update. Now, there's a natural objection to this, and that is, wait a second, we would hope that for ordinary sequentially consistent programs, we should reduce back to a wiki grease, right? So we'll have certain operations that we'll call an operation a barrier if it happens to have an update that conflicts with every other operation of the program. And you can see how to encode this with ghosts. Just have some sort of let's say not every operation of the program, all barriers pairwise conflict. So just have some chosen location out here in Ghostland. Any operation that's a barrier, add to its update a change to that, okay? So that they conflict. So barriers have to be ordered one way or the other. So we can strengthen the non-interference rule slightly. If this guy, the preceding operation, is a barrier, then if this guy is also a barrier, you get to use its guard in proving non-interference. I just told you. So a barrier is simply, it's defined semantically. It's just an operation whose update, we're going to just choose some set of things to call barriers with the condition that any two barriers, their updates conflict. Okay? Yeah, we have, sure, it's ghost. Just have one for every operation instance. Okay? So that gets us back to a regular wiki grease if everything's a barrier, which means you have sequential consistency. So there's the proof rule. Now, of course, in real reasoning, if you're building a real verifier, you don't use a wiki grease, right? It's not modular. We simply use a wiki grease to understand what's going on. And the way you actually implement it is you replace the interference with something like an object invariant that's visible. So you have some object invariants that limit the interference you're seeing, and you use those to prove the non-interference. And that's just standard program reasoning. Basically, when I write something here, this predicate has to be stable. I have to know that taking a scheduler boundary won't destroy this thing, and you use that by whatever global invariance, typically two-state invariance in, say, VCC, you have to prove that. Okay? So everyone understand the programming logic. So theorem 1 for any cut, suppose you have an annotation that satisfies these conditions. Take any cut, okay? Then for every edge going from inside the cut to outside, the label on that edge is satisfied, okay? And this is true for any execution. So this really is exactly what you would expect in a sequentially consistent world, but it still holds true in this funny world too, okay? And you just prove this by induction on the graph, as you would expect. Okay, so this is sound. Okay? Now, let's get back to the problem of why we weren't able to prove this. Well, how could we prove this? Can someone suggest a way we might prove it? Suppose we could use auxiliary variables. And suppose we were sequentially consistent. How would we prove false at the end? Any ideas? Just someone with a...
Enumerate all possible schedules, permutations.
Okay, so one possibility is you could have a program counter for each thread, right? So that you could tell where you were and write that invariant that says if I'm at this place and he's at that place, I'm in one of the states that's reachable, right? And that would obviously satisfy the conditions. That would require we add a ghost update to the program counter of each thread in each of its updates. And because that invariant has to be everywhere, we would have to talk about that auxiliary variable in other threads. This is clearly not sound, right? This would get us to sequential consistency, just as you say. So the reason that you can't do that is, first of all, if it's just a local variable, right, then you can't mention it in other places, okay? Now, the second reason you won't be able to do it is that, remember, you're depending on the operational semantics, right? But that depends on using these guards. And so, in fact, it will fail the non-interference test when you try to go past these guys, because you won't get to use the guards. So, that won't work. But let's try to just think actually about the particular program. What would we do? We would track perhaps who won the race. How could you do that? Introduce an auxiliary here, let's say, where we call W that's initially 0, and at this place, if W is still 0, set it to 1, otherwise leave it alone. Over here, if W is still 0, set it to 2. Okay? So W will keep track of who won the race for us, right? And now this is the place where I need to ask whether I should show slides. If you want to see the actual proof that would use that, I have them on slides. But if you'd rather not bother seeing it and you just trust that, yes, it could be proved, then I'll just use this. Would you rather see slides or keep going with board? Board? Okay. So that's one possibility. Add those updates to W. Now, what went wrong here? What went wrong here was we took two writes that were non-interfering, that commute, took two updates that commute, and adding those ghosts, we ended up with updates that do not commute. That means what justifies ghost variables, right? What justifies ghost variables is that the program without the ghosts simulates the program with the ghosts, okay? That means every execution of the program without, you have to be able to turn into an execution of the program with. Because the program with added an additional edge requirement, this thing, which is an execution of the program without the ghosts, is not going to be an execution of the program with the ghosts. No. I didn't assume anything. I just said simulation is still just...
But you wanted to add,
Well, what I'm trying to do, obviously I shouldn't be able to prove this. What I'm trying to get insight to is why adding ghosts will break, and to get an idea of what the conditions on adding ghosts should be. So, the rule is that you can't add ghosts in a way that's going to create a new conflict that wasn't there before, okay? So we can't add these conflicting ghosts, with one exception, if they're both barriers, okay? So what does that tell us? Once we construct the proof with these ghosts here and here, we know that if we wanted this program to work the way to prove false at the bottom, we can do it if we simply turn these things into barriers. So on x86, you can achieve that by having them flush the store buffer. Okay? This is the other part of the program. The way you teach people to program to weak memory, they start out with the program, they prove it assuming sequential consistency. Maybe they do several proofs. Now you look at the proof, you see how you used ghost variables. That gives you additional obligations about how you have to add barriers to your program. Okay? And that gives you a weak memory program. If you didn't need to use ghosts at all, for example, you don't need any ghosts to prove producer-consumer, then you're fine. You don't need any barriers at all. Release, load, acquire, store, release is good enough. How am I on time? Okay. Let me just go through other possibilities. By the way, I won't go into, I'm describing the constraints in terms of a wiki Greece, but all of these can be done in a modular way also by, if you want to force two things to be both the same, you simply say, all right, this location has a certain, you need some sort of capability to use it such that that only the right combination of guys can race. But I won't go through this now. I can show anyone who's interested. But all of this is being put into VCC, is methodology.
So, if you introduce barriers to those points, aren't you also constraining out a whole bunch of potential...
That's right. So that's maybe not the best thing to do.
Okay.
You could do a different proof that puts barriers here and here, or you could put a different proof that has a ghost update here and here. Now, by the way, the one last possibility is it turns out you can prove this without introducing conflicting ghost updates. You can do right here something like W1 gets 1, and here W2 gets 1. And with an appropriate annotation, get down here X and W1 and not W2, okay? And the corresponding thing over here. But once again, you will fail the non-interference test because this thing, without getting to use this guard, will break what you put there. So again, that gets you back to putting barriers on these, okay? So let me show one other example. Where's the eraser? Are there any other questions about this one?
The way you can add ghosts and say that if you put things in these various places, that would force these restrictions. And so that will allow you then to prove, if you
Gives you a
those
soundproof system.
if you get a soundproof system for the TSO.
No, for the weak model.
For any weak model.
Not necessarily for any, but for any which you can come up with a reasonable set of things that
So is
sound.
there some way of characterizing what weak models it does these sound for? Or?
Well, so first of all, this model that I've described so far is sound for TSO as long as you don't have one thing. And actually I'll show you the one counterexample. It's if you have a write that's not a read-modify write that's racing with another write to the same location. And that write, the bare write, is not a barrier. So here's the this half on the other now? This is wet. Uh-oh. That might not be a good idea. And if anyone's interested in the VCC encoding of these restrictions so that it's modular, just, oh, thank you. Just come and ask. So here's the bizarre one that really had me bothered for a long time. And my instinct for the last couple of years was simply not to allow these racy bare rights because I haven't ever seen a useful piece of software that has them, although I know of one place it could be useful. But now I think there's a reasonable way to do it. So suppose you have a thread that first stores 1 in y, and then he stores 1 in x, and then he reads x is 2. And the store of x getting 2 comes over here. And now, this is a bizarre execution because, right, you see, even though different threads can see stores in different order to different locations, you expect every thread will see the same order of stores to any given location. So the stores to X, you have to see the same order everywhere because otherwise you might end up in different states in different threads, right? So the fact that you assign to X 1 here and then you see it's 2 means this assignment has to come in the modification order of X after this assignment. And this, of course, comes before this, and yet he didn't see it. This can actually happen on x86. This program can happen on x86. But, logically it sucks, right? The idea that these guys will have to be ordered one way or the other just doesn't hold for writes that are just simple writes. If this thing was a read modify write where it first read x was 1 and then made it 2, then it would see y. Then this is impossible, even though it's exactly the same execution. And this is just of hardware, okay?
Actually execute out of order in the processor.
It's not so much that. These two can't. These two? No. This is on a TSO machine. Even on x86 this can happen just because of the timing of when things go in the buffer. As an exercise, you can find it. So, now, once again though, how would you prove false down here? Well, it turns out the way you would do it is you would keep track of who won this race. And the way you could keep track of who won this race is by adding a little ghost update like Z gets 1 right here, okay? And as an exercise, once you have this, go ahead and fill in the annotation to prove false down at the bottom. But now, this is a little funny because on this variable before, this guy was being completely obliterated by this write. But now with this assignment to the ghost, it's not being obliterated anymore. We're leaving behind a remnant. So it turns out the only restriction you need to get back to soundness, even allowing these racy writes, and to get a thing that's completely sound for load, acquire, store, release on x86, is to say that if you're in a racy write situation, okay, then the bare write has to obliterate this ghost, has to obliterate everything the other write does so that it disappears, okay? And you can do that by simply classifying your ghosts. You have ghosts that are attached to locations. So Z would be attached to the location of X, And this guy would be obliged to actually write over Z at the same time, obliterating the previous side effect. And there you get back to soundness. And that's basically the end of the story. It's not quite to the C11 memory model, but it's getting close. C11 has some more stuff. I don't expect to be able to handle the unsequenced atomics, but I do expect to handle the rest of the C11 memory model in the next VCC. So that's it. Thank you.
Questions?
So can you handle the power model?
Well, if it handles C11, the C11 memory model is designed to handle that. The main problem there, I mean, it's not a problem in principle. The problem is this idea that happens before only follows causal connections means that at a given point in the program, you're morally obliged to keep track of which variables have causal output to which stuff coming in, and that's just like a mess. So it's just a question of, can you make something decent? But it's okay, if it's just sound for the things people have to do. I'm not so concerned about completeness because, in reality, a verifier that's working by hand annotation is far from complete anyway. It's the practical utility and integrity of the model, and that it's something that you can teach students. That's what I like about this. The main reason that this is an urgent thing is I'm teaching a multi-core programming course this spring, and I thought that I should actually know what I'm talking about before doing so.
But I disagree with the completeness, because in some sense you had completeness in your head, because you said, okay, why can't we prove it? That's it. If you have a proof that it's not complete, then there are problems in which you
Well, no, that...
be able to prove that you can, because the method is not complete.
Right, but that was a facetious thing. I didn't want to be able to prove it. It was that it seemed paradoxical that we couldn't prove it because of completeness of a wiki Greece.
But that's the point. If you had a method that's not complete, then there are problems that you say, well, I need to be able to prove it, and I can't because the method is too weak. So the idea is that in principle, the method don't tell you how to prove it. You still have to be inventive and come up with the right rows, the right and the right. But if the method is not too weak to start with,
It does mean there's potentially an architectural problem. Just to close that up, the system without the races, the system that I showed for programs that don't have the bare right races is in fact complete for x86. Well, it's complete for this memory model. You could argue that being complete for x86 TSO shouldn't even be a goal because it's just some random collection of garbage people put together, whereas that memory model was really sort of coherent. By the way, the memory model where you have this, in order to allow racy things without ordering them in the execution, you have to have the modification order as part of an execution. And that complicates the proof a bit, which is why you get this obliteration requirement. But I haven't proved completeness of that yet for that model. But I think it should be provable.
So one thing that people have looked at, I guess, is for very small models, is they kind of like do a proof on the sequentially consistent program, like you just provide with some wiki or something else. And then they have theorems that basically say, under a particular model, if you don't have certain races, then your program is
Right. Reduction theorems. In fact, that's what we use. I think I did the best one currently for x86 TSO. That's what we used in VCC for all of the verification in the last 10 years. The reason for that was that there were only a couple of places where we didn't have sequential consistency, but more importantly, I didn't have a way to handle non-sequentially consistent code because invariants seem to completely depend on it. And the strange thing is, they really don't. It's the ghosts that are the problem. As long as you watch out and control your ghosts, you can use invariance reasoning without any SC. Sorry.
So, while I find this, potentially interest to a small number of people like me who program for weak memory, you started out by saying, I'm going to do this so that, you know, people more generally can program for weak memory. My experience has been that, you know, even if you take, you know, PhD researchers and give them sequential consistency,
They can't do it.
they can't handle it.
Right, so I'm not saying that it should be everybody. I'm saying that everybody that you should trust to program to sequential consistency, you should be able to train so that they can also program to these weaker models.
What you're saying, you're quantified over an empty
Yeah, not an empty, just a small. Oh, but you have to understand that the set of people who are considered able to program to sequential consistency is like massive compared to the number of people that are generally considered able to program to weak memory. Weak memory, you know, the way they talk about it is it's added to the C11 standard for about 10 people to be able to write libraries. And that everyone just says over and over, no, 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 programmers shouldn't be using this. Make it syntactically hard so they don't do it by accident. You know, it's courting disaster. And the claim is that it's really not so impossible once we, or another way to look at it is that this provides a big chunk of leverage for using assertional reasoning to reason not just about weak memory, but also about SC. Because once you use that for SC, and it really is the best way, you get weak memory almost for free by just looking at where you use your ghosts.
So I have one more question. So you actually imagine that people will come up with several proofs using different instrumentations with ghosts, or do you think people will already have in mind where they want to put their barriers?
They probably will have some idea of, you know, can I come up with a way? Maybe they'll have an idea, I barrier here and here, and now I'm trying to find a proof where I'm only allowed to put the ghosts there and some other restrictions. I mean, the restrictions are, especially in the modular verification situation where you don't have the whole program, it's a little bit more complicated. But basically, yes, the idea is they sort of try to engineer a proof.
So what will VCC do when you violate this rules? Will it tell you your proof is invalid, or will it tell you it's a valid proof and now you only have to put a barrier there?
No. I mean, you'll have to put the barriers. What you'll do is you'll say, we'll use sequential consistency. It'll say, good proof, congratulations, you verify. Now you can see textually where you updated your ghosts. And now that's going to tell you. Now you go ahead and add a barrier there, go to weak memory, and it'll say, wait a second, you failed to do this check, whatever.
Okay, so let's thank Ernie again. So that takes us to the end of the technical program. Martin has a few final remarks, I think. Or
Yeah. I can say a few things. Okay, yeah. So yeah, so this concludes the workshop. So thank you very much for coming. Good attendance. And where is Marlies? Marlies is there. So thank Marlies for all the organization. She did